Thank you for watching my presentation. I will present the work in which we explore the problem of multiple drone coordination to obtain reliable and timely situational awareness in high-res fire scenes. First, let's see some background information about high-res fires. From the statistics, we can see that each year from 2017 to 2019, fires in residential buildings have caused a huge damage in civilian life and property. In residential building fires, high-rise buildings present unique challenges to firefighters due to their unreasonable tall floors, limited egress pathways, and water supplies. Besides, the fire spread inside the building sometimes is unpredictable due to the impact of the internal airflow, stack effect, and the wind conditions. Also, firefighters are lack of the situational awareness of the fire scenes due to their limited access to the buildings. All these factors increase the difficulties in the high-rise firefighting. Another bad news is reported that nowadays there are significant high-rise buildings are at risk of serious high-rise fires due to their combustible exterior wall assemblies. This kind of bad construction material will cause the fire rapidly spread upon them. Above all, we know that high-rise firefighting is difficult and there is high risk of high-rise fires. Next, we want to help firefighters. Here we focus on improving their situational awareness of high-rise fire scenes. We abstract some events, the awareness of which are crucial in firefighting. First, firefighters should detect the fires and track fire spread. Humans should be detected and monitored by firefighters for human rescuing. Besides, they should detect open windows or doors, whose state will impact the ventilation status of building. Being aware of this kind of events is important for the incident commander when predicting the fire spread and making firefighting plans. To get the information of those events, in our scenario, we use drones mounted with cameras flying around the high-rise buildings to capture images through windows or balconies. Drone has distinct value in extreme conditions because of its properties like flexibility, scalability, easy to deploy, and quick movement, which can support real-time data collection. There are several special concerns for drone-based monitoring in high-rise fires. First, for monitoring heterogeneous events, we need to consider their diverse properties like dynamics and significance. To support continuously monitoring using limited number of drones, drones here should repeatedly cover some areas during their monitoring process. Another interesting issue should be noticed that when capturing images, if a drone goes close to the building facade, it will get data with higher accuracy for detecting events, while smaller coverage area. If a drone flies further away to the building, the images it captured will cover a larger area but have lower data accuracy. How to make the trade-off between the coverage and data accuracy is another concern in this work. To explore this concern, we define the concept of observation to indicate the drones capturing images. We named call screen observation to denote drones capture images at distance relatively far away from the building facades. In contrast, fine-grained observation means taking images when drones are close to the building. Here we summarize the main contribution of our work. First, we design a multi-drone coordination system called DragonFly to manage drone-based monitoring in our scenario. To support this system, we formulate the multi-drone waypoint scheduling problem to make a flat plan of drones to do call screen and fine-grained observations to improve their situational awareness. We also developed the algorithm to solve this waypoint scheduling problem. To evaluate our proposed algorithms, we simulated different high-rise fire scenes and implemented the prototype of DragonFly system. Next, I will introduce Dragonfly system. Once a fire is reported to the fire department, firefighters will come. We design the Dragonfly system in the incident command set, which is located in a fire truck. In Dragonfly, we have an incident manager who works for generating, monitoring tasks for drones to monitoring the fire scenes. The objective of each monitoring task is to detect an event in a specific area on the building facade, which contains one or more windows or balconies. The event can be the presence of fires, humans, or open windows, or the changes of their status. All tasks will be transmitted to a component called drone coordinator, which works to generate the waypoint sequence for multiple drones. Here each waypoint is a tuple of a 3D coordinate and a camera orientation. The drone coordinator uses sequences of waypoints to specify the flight paths of all drones. As images being captured by drones, they, along with the drone's state information like power state and locations, will be transmitted to the data receiver and analyzer component, where the collected images will be analyzed for detecting the events specified by monitoring tasks. All detected events would be recorded into a perception table that logs the event and its detection time and location. As time goes, images would be continuously transmitted to our system. Perception table would be updated by the new detected events. And the monitoring task of drones also would be updated correspondingly. Then the updates of tasks would be inputted into the drone coordinator, which would update the waypoint sequence of drones if needed. Due to the dynamics of the fire scene, instead of making a long-term plan, the drone coordinator makes the short-term flight plans periodically. Also, the drone coordinator would replan the flights once the monitoring tasks are updated or the number of drones is changed. In each planning, the drone coordinator would solve a multi-drone waypoint scheduling problem, which aims to generate waypoint sequence for drones to fulfill all monitoring tasks in next plan duration. To support this functionality of the drone coordinator, we formulated and developed techniques to solve MWSP. Next, I will show its problem formulation. The assumptions in this problem include: first, the high-rise building structure are known by firefighters. There are reliable communication between drones and the incident command site, which means there is no delay and data loss during data transmission. Sensing capability of drones are homogeneous. Also, the drone's camera orientation are always perpendicular to the building facade. Image processing methods in data analyzer for all events exist, and the accuracy for detecting events under cold screen and fine-grained observations are given. Next, we design some symbols in our problem. First, we redesign the monitoring tasks. Instead of using the symbol version that only contains the event and the monitoring areas, here we add 3 additional parameters, which are the task generation time, significance, and frequency. The significance presents the emergency level of the task, and the frequency indicates how often the event of the task should be observed by drones, which is specified based on the event dynamics. We design monitoring areas to specify the location of detected events, which is a bounding box on the building facades, which contains one or more building or balconies. Given the building structure, we can get all monitoring areas on the building facade. Then we can get a set of waypoints, which cover all monitoring areas at a different distance to building facade for close and fine-grained observations. We can specify a path between 2 waypoints by visibility graph method. Also, we can know the coverage correlation between waypoints and all monitoring areas. Given the accuracy of the image processing method, we can get the accuracy for detecting events at each waypoint. Before going to the next symbol, let's recall the main objective of Dragonfly system, that is to improve the situational awareness of the firefighters. To evaluate the level of situational awareness of each task at a specific time, we introduce the information accuracy, which equals the probability that a perception of an event of a task is the same as its current real state. Considering the dynamics of the event, we rule that the value of information accuracy decays as time following the geometric distribution using the task frequency as the parameter. Besides, we define the concept of effective observation, which enable ICS to ignore some detected events from the observation of lower accuracy compared with previous perception. Finally, we define the area under curve AUC, which is the integral of the information accuracy to quantify the overall situational awareness of a task during a time duration. Next, we define the waypoint schedule parameter X, which presents the waypoint sequence of multiple zones during the next plan duration. Given the waypoint schedules, we can deduce the information accuracy of all tasks during next plan duration. By now, we can formulate our multi-zone waypoint scheduling problem. The input of this problem are shown in this figure. Its output is a waypoint sequence for multiple zones in next plan duration. The objective is to improve the situational awareness of all monitoring tasks, considering task significance. Here, for each task, we use the AUC value of it during its generation time to the end of the plan duration to evaluate the situation awareness level of it. The reason why we take the AUC value before current time into consideration because we want to consider the historical observation status of tasks when we make the flat plan for the future duration. Next, we get the mathematical formulation of our problem. Here we skip the discussion of the constraints and focus on the objective function. Here we notice that the red part is for normalization, and the AUC value is weighted by the task significance. The reason for this is we want to prioritize the monitoring tasks according to their significance. The higher significance level it has, we will put more effort to improve their situational awareness. Besides, we maximize the weighted minimum AUC value for all tasks to improve the overall situational awareness, considering their task significance. This problem is NP-hard. We can prove that by reducing the traveling salesman problem to a special case of our problem. Considering the NP hardness of multi-zone waypoint scheduling problem, we propose a two-step approach to heuristically solve it. We split it into two steps. The first step, we solve a AMT problem, which aims to allocate a set of tasks to n zones. Considering the collision avoidance issue, we decided to allocate the tasks based on the spatial location of the monitoring areas located in. Namely, we changed this problem to a story that given all monitoring areas containing monitoring tasks, and we want to partition them into n disjointed subsets. We define the expected time consumption for each subset, which equals the expected traveling time for a zone to observe all tasks in the subset for desired number of times. The visiting time for each task is generated based on the task frequency and significance. Then the objective function of this problem is to minimize the maximum time consumption for all subsets. To solve this problem, we propose an AMT algorithm where we first solve the K-MAD-OS problem to get the initial partition of monitoring areas. Next, we utilize the local search method to improve the initial partition. More specifically, we iteratively generate a group of neighbors of current partition using two operations, which are transferring and swapping. Given the neighbors, we will replace the current partition using its best neighbor, who leads to the minimum value of our objective function. This improvement would stop until there is no good neighbor or running time exceeds a time limit. We also propose a lightweight algorithm for task allocation, which is used to handle the updates of the tasks or number of drones during task execution. After the task allocation process, we enter the second step of our approach. Where given the task allocation, the waypoint sequence for each drone are generated in a parallel manner. Each operation solves the dynamic waypoint scheduling problem. Actually, the dynamic waypoint scheduling problem is a special case of multi-drone waypoint scheduling problem, which has a single drone. Next, we propose DWSF algorithm to solve dynamic waypoint scheduling problem. There are three main steps in this algorithm. In the first step, we heuristically select a waypoint for covering all monitoring tasks for coarse and fine-grained observations. Next, we start to create a waypoint sequence. During this phase, we will first check if there are tasks with the AUC value equals 0, which means those tasks haven't been covered. If yes, then we will enter the fast coverage phase, where we heuristically select the waypoint to cover the most tasks with AUC value equals 0. After some time, when all tasks have been covered at least once, we will enter another phase, where we heuristically choose the next waypoint, which can maximize the ratio between the improvement of minimal weighted AUC with the traveling time. Next, we will evaluate our proposed algorithms. To evaluate our proposed algorithms, first, we implement 4 comparative algorithms to compare with our DWSF algorithm. The DWS algorithm gets the DWSF without fast coverage phase. The minimum improvement algorithm will greedily select the waypoint that improves the task with the lowest AUC value in each iteration. NN and MST algorithm are 2 heuristic methods for solving traveling salesman problem. Besides, we implement the K-MedOS method to compare with our AMT algorithm. Here we propose file performance matrix. Missing event counts the number of the undetected events besides on our perception table. Minimum weighted AUC is the objective function of our multi-drone waypoint scheduling problem. The weighted accuracy, here we get the accuracy of each task by sampling the information accuracy in every 30 seconds. Then we use the average value as the accuracy of this task. Then we compute the minimum accuracy among the tasks in each significance level. Finally, the weighted accuracy is the weighted sum of them. The function of the weighted reliability is similar with the weighted accuracy. Here we just replace the accuracy with the task reliability. For each task, its reliability is the ratio of the sampled information accuracy whose value exceeds a specific threshold. The last matrix is the running time of the algorithm. In the simulation setup, here we create the high-rise building based on the layout of DBH building in UCI campus. To generate the events, we simulated the fire dynamics by using an existing fire spread model in literature. Also, we simulate the dynamics of human and opening status of windows based on the probability model. We simulate the incident manager in SCS using a high-res firefighting menu, and implement the perception table to record all detected events in our simulations. From the simulation result, we can see that, first, if we use the same task allocation method, our DWSF method always leads to less missing event during the whole monitoring process. Then we fix the waypoint method to compare the task allocation methods. We can see that the AMT algorithm can lead to less missing event compared to the K-MedOS method. Next, we fixed the task allocation method to evaluate the waypoint scheduling methods and the different number of drones. From the results, we can see that our DWSF algorithm leads to minimum with missing events, highest weighted AUC value, highest weighted accuracy, and weighted reliability. We also explored the performance of task allocation methods and a different number of tasks. From the results, we can see that using the same waypoint scheduling method, our AMT algorithm always have better performance on these 4 metrics. Finally, we get the running time of our local update method plus the waypoint scheduling methods. From the results, we know that our LU plus DWSF algorithm has relatively low running time, which is suitable to be used for real-time decision-making for flight replanning during the task execution. Finally, we get the conclusion of our work. In this work, we designed the DragonFly system to improve the situational awareness of firefighters in high-rise fire. To support this system, we formulated the multi-drone waypoint scheduling problem, and we propose a two-step approach to solve that. The simulation results show that our proposed method has superior performance compared with other algorithms. In the future work, we will explore the image processing methods for more events in this high-rise fire scene. Also, we plan to utilize this system in some other scenarios like wildfires, which have some other challenges in data collection, like poor network conditions. Thank you for listening.